In today's lesson, we're going to learn how to solve absolute value equations and absolute value inequalities. We're going to start with absolute value equations, and we'll first look at a very basic example. This absolute value equation has two solutions. One solution is that x equals 5, because if you plug in 5 for x, you'll have the statement the absolute value of 5 is equal to 5, which is true. The other solution is that x equals -5, and this is a solution because if you plug -5 in for x, you'll have the absolute value of -5 is equal to 5, which is also true. And we'll see that for most of our absolute value equations, we'll end up with two answers like we did here. Now that we've seen a basic example, let's write down the general rule for solving absolute value equations, and then we'll look at some more complicated examples. If you have the absolute value of some quantity u is equal to a, there will be two solutions. The first solution will be given by just removing the absolute value bars and writing u is equal to a, just like the first solution here was x equals 5. And the second solution will be given by adding a negative to the right side. U is equal to -a, just like this second solution was x is equal to -5. So this is the general rule. Now let's look at a few examples. We'll start with this absolute value equation. The first step when we're solving absolute value equations is that we need to isolate the expression containing the absolute value. For this particular problem, the expression containing the absolute value is this expression right here. And this absolute value expression is already isolated. There is nothing outside of the absolute value bars on this left side of the equation. So I put a check mark here because the absolute value expression is already isolated. Okay, I've copied down our expression into step 2. For step 2, we're going to rewrite the equation as two separate equations with no absolute value bars. And this is where we use this rule here. The first equation that we write is the easiest, because for this first equation, all we do is copy down this exact expression, but remove the absolute value bars. Just like we did up here, we copied down this exact expression, but we removed the absolute value bars. So that will give us 4x plus 3 is equal to 1. Then the second expression we write, we're only going to make one change. So we still copy down this exact expression, but remove the absolute value bars. And let's look back up here. Notice for this second equation, we added this negative. And that's exactly what we do here. For this second equation, we need to make this one negative. Now, before we move on, let's ask ourselves, why do these two equations give us solutions for this problem? Well, in order for this to be true, this quantity inside the absolute value bars, the 4x plus 3, must equal 1. Because then we would have the absolute value of 1 is equal to 1. That's exactly what we wrote here. We said that this quantity, 4x plus 3, must equal 1. The other possible solution is that this quantity inside the absolute value bars could equal -1, because the absolute value of -1 is also equal to 1. Well, that's exactly what we wrote here. We said that this quantity, 4x plus 3, could also equal -1. Now, we just need to solve these two equations, and we'll have our two solutions. To solve this equation on the left, let's subtract 3. That will leave us with 4x is equal to -2. Then we can divide both sides by 4. And that will leave us with x is equal to -2/4 reduces to -1/2. Then let's solve this equation on the right. So we have two solutions here, and you can always check your solutions by plugging them into the original problem. Plug in -1/2 for x and make sure that gives you 1. Then plug in -1 for x and make sure that also gives you 1. And you can write your final answer like this, or if you're required to write your answer using solution set notation, you would write your answer like this. And with solution set notation, the order that you list the answers doesn't matter, so you could flip around those numbers if you'd like. Let's take a look at another example. The first step when you're solving absolute value equations is you want to isolate the expression containing the absolute value. So I've copied down the original problem and I've highlighted the part that we want to isolate. We want to isolate this absolute value expression right here. Everything outside of these absolute value bars on the left side, we want to get rid of. So we need to get rid of the 6 and the negative 2. To start, let's subtract the 6. And that will leave us with negative 2 times the absolute value of 3x minus 2 is equal to negative 14. Now we've almost isolated this absolute value expression, but the last step is we need to get rid of this negative 2. This is read as negative 2 times the absolute value of 3x minus 2. So the opposite of multiplying by negative 2 would be to divide by negative 2. And that will leave us with the absolute value of 3x minus 2 is equal to 7. So we've completed step 1. We've isolated this absolute value expression. For step 2, I've just copied down this exact expression. Now we want to rewrite this expression as two separate equations with no absolute value bars. The first equation is the easiest. We just copy down this exact expression, but we remove the absolute value bars. That gives us 3x minus 2 is equal to 7. The second equation is almost as easy to write. We start by writing exactly what we just wrote, but the one change we make is that we make this 7 negative. Now that we've written our two equations, now we just need to solve them to get our final answers. I'll first solve this equation on the left. And if we solve this equation on the left, we get x equals 3. Now let's solve this equation on the right. And if we solve this equation on the right, we end up with x is equal to negative 5/3. And we can write our answers like this, or if we're asked to write our answer using solution set notation, our answers would look like this. Before we move on to the next example, I want to talk about the two most common mistakes for a problem like this. One very common mistake is that students will try to distribute the negative 2. But the distributive property is really only intended for problems involving parentheses. If these were parentheses, you could certainly distribute the negative 2. But the distributive property is really not meant for absolute values, so please don't try to distribute across absolute value bars. The second most common mistake is that students will see a problem like this, and they will right away start to draw their two separate equations. Do not write your two separate equations until you've first isolated the absolute value expression. So first isolate. Only after you've isolated the absolute value expression do you want to then write your two separate equations. Let's try one last related example before moving on. We're going to see that we get a different type of solution for this problem here. The first step is to isolate the absolute value expression. So I've just copied down the original problem. In order to isolate this absolute value expression on the left, let's subtract away the 7. And that will leave us with the absolute value of 5x plus 3 is equal to negative 2. Now, for step 2, normally, once we've isolated our absolute value expression, we write our two separate inequalities. But we're not going to do that here. We're actually going to stop completely. The absolute value of a quantity always gives you a positive result. So an isolated absolute value always needs to equal a positive number. You can plug in any real number for x here and compute this expression, and you'll always get a positive answer because the absolute value always makes this quantity positive. There's no number in existence that you could plug in for x that would give you a negative result. So I've written here, an isolated absolute value expression can never equal a negative number. So our final answer here, you could write as no solution. You could also write this symbol, which means no solution. You could also draw these empty brackets, or you could write empty set. Next, we're going to solve equations that involve two sets of absolute value bars, like you see here. We'll start with a very basic example. This problem here has two solutions. One of the solutions is that x equals 9, because if we plug in 9 for x here, we'd have the absolute value of 9 is equal to the absolute value of 9, which is definitely true. The other solution would be that x is equal to negative 9, because if you plugged in negative 9 for x, you'd have the absolute value of negative 9 is equal to the absolute value of positive 9. This would be a true statement because the absolute value of negative 9 is equal to 9, and the absolute value of positive 9 is also equal to 9. Now that we've looked at a very basic example, let's write down the general rule, and then we'll look at some more examples. In general, if you have the absolute value of some quantity u is equal to the absolute value of some quantity v, you'll have two solutions. The first solution will be given by just removing the absolute value bars and writing u equals v, and the second solution will be given again by just removing those absolute value bars, but also by adding a negative to the right side, just like we did up here. So let's look at an example. Now, when you're solving absolute value equations, the first step is you want to isolate the absolute value bars, but for problems involving two sets of absolute value bars, these absolute value expressions will always already be isolated for you. I've started by just copying down the original given problem, so we can start by rewriting the equation as two separate equations with no absolute value bars. The first equation is the easiest. We just copy down this exact expression, but remove the absolute value bars. That will give us 5x plus 3 is equal to 12 minus 4x. The second equation is almost just as easy to write. We start by copying down this exact equation that we just wrote, but we make one change. We make the quantity on the right negative. So to make this whole quantity on the right negative, I'm going to add parentheses around it and then add a negative. Now, why will these two equations give us solutions for this problem? Well, let's think about it. If this quantity inside the absolute value bars is equal to this quantity inside the absolute value bars, which is exactly what we've just written right here, then you would be taking the absolute value of two identical quantities. So that would give you a true statement. This side would be equal to this side. The other possibility is if these quantities inside the absolute value bars are equal but opposite in sign, which is what we just wrote here, then you'd be taking the absolute value of two identical quantities. The only difference between those quantities is that they would be opposite in sign. Well, the absolute value bars make everything positive. So the absolute value of this quantity would definitely be equal to the absolute value of an identical but opposite quantity. So now, to get our final answer, we just need to solve both of these equations. I'll start by solving this equation on the left. So when we solve this equation, we get x equals 1. Now let's solve the equation on the right, and let's start by distributing this negative. That will leave us with negative 12 plus 4x, and then we'll bring down the 5x plus 3, and we'll continue to solve for x. And we get the solution x is equal to negative 15. So we can write our final answer like this, or we can write our final answer in solution set notation like this. Now again, here we have an equation involving two sets of absolute value bars, and for these types of problems, each set of absolute value bars will already be isolated. So we won't have to worry about isolating. We can jump right into writing our two separate equations. The first equation is the easiest to write. We just copy down this exact expression, but remove the absolute value bars. Then for our second equation, we can copy down this exact equation that we just wrote, and then we're going to make one change. We're going to make this right side negative. And make sure you add these parentheses to ensure that you're making the whole right side negative. Now technically, when you write this second equation, you could make either the left side negative or the right side negative. It doesn't matter either way, but just for consistency, I always like to make the right side negative. Now we can go ahead and solve these two equations. I'll start with the equation on the left. We like to get x on only one side of the equal sign. So I'm going to start by adding 2x. Now x appears on only one side of the equal sign. Now we'll proceed to isolate this x. And we get the answer x equals 2. Now let's solve this equation on the right, and we're going to notice we get an interesting solution here. First, I'll start by distributing the negative. Now, when solving equations, we like x to appear on only one side of the equal sign, not both. So I'm going to subtract away this 2x in an effort to get x to appear only on one side of the equal sign. Now, something interesting happens here. These x's cancel, and we're just left with -3. And these x's cancel, so we're just left with -5. You might solve this equation differently and get a slightly different answer here, but no matter how you solve this equation, you will always end up with a false statement. That means that there is no solution here. This equation has no solution, but that doesn't mean that the entire problem has no solution. There is one solution, x equals 2. It's just typically absolute value equations have two solutions, but this particular equation only has one solution. So you can write your final answer like that, or you can write your answer in solution set notation, which would look like this. So far, we've been solving absolute value equations. You know you have an equation if you see an equal sign in your problem. Next, we're going to look at absolute value inequalities. So these problems will have inequality symbols in them instead of equal signs. But before we get into these types of problems, I want to make sure that we understand the definition of absolute value. A lot of people just memorize that absolute value bars mean that you always get a positive answer. But the definition of absolute value is the distance from 0. So if we're asked to find the absolute value of -3, the absolute value is asking us, what is the distance between -3 and 0? Well, -3 is 1, 2, 3 units from 0. So the absolute value of -3 is equal to 3. Distance is always positive. And so since absolute value is defined as being the distance from 0, absolute value always gives us a positive answer. So we're going to start with a very basic example. Let's suppose we were asked to solve the inequality, the absolute value of x is less than 4. Well, what does this actually mean? Remember, absolute value is the distance from 0. So this is saying the absolute value, or the distance from 0, must be less than 4. So this is asking us to find all real numbers, x in this case, that have a distance of less than 4 units from 0. So let's find the set of all numbers that have a distance of less than 4 units from 0. Any number between -4 and +4 will have a distance of less than 4 units from 0. For example, 3 has a distance of 3 units from 0, which is less than 4. -2 has a distance of 2 units from 0, which is also less than -4. How could we write this mathematically? Well, x can be any number between -4 and +4. This can be written mathematically in this compact notation, which says x is between -4 and +4. We're going to soon see more complicated problems where we don't just have x here, but we have an actual expression. So then we'll further solve. But for this particular example, our x is already isolated. There's nothing more that needs to be solved. If we were asked to write this answer in interval notation, we always start with the lowest number, which is -4. Then we list a comma and list the highest number, which is +4. So if we see absolute value inequalities involving a less than symbol, like we saw here, or a less than or equal to symbol, we're going to solve them by rewriting the problem in this form. And we're going to refer to this form as a compact double inequality. Let's look at some more complicated problems on the next page. So for the next two examples, we're going to be looking at absolute value inequalities involving less than or equal to symbols. We'll first write the general rule, and then we'll look at a couple examples. If you see an absolute value inequality involving a less than symbol, to solve it, we rewrite it using a compact double inequality, which looks like this. U is between +a and -a. If we see an absolute value inequality with a less than or equal to symbol, we rewrite it in this same exact form. The only difference is we replace these less than symbols with less than or equal to symbols. So let's take a look at an example here. With any absolute value equation or inequality, the first step is we need to isolate our absolute value expression. So I've started by copying down this original inequality, and I've highlighted this absolute value expression, which is what we want to isolate. To isolate this absolute value expression, we just need to get rid of this 3. So let's divide by 3. And now we have our absolute value expression isolated. Step 2. If your isolated absolute value expression involves a less than or equal to sign, which is the case here, then we want to rewrite the inequality using a compact double inequality. So I've just copied down the expression that we left off with. Now, what does this actually mean? Remember that absolute value means distance from 0. So, since we're taking the absolute value of this quantity, that means that this quantity here must have a distance that's less than or equal to 3 units from 0. In order for this quantity to be less than or equal to 3 units from 0, the quantity 2x plus 1 must be between 3 and negative 3. So this is the compact double inequality that we write. Now that we've written our compact double inequality, now we just need to solve it for x. In chapter 2.5, we learned how to solve inequalities that are written in this compact notation. To solve inequalities like these, you want to isolate x in the middle. So to isolate x in the middle, let's start by subtracting 1, and whatever you do to the middle, you have to do to the left and the right side. So we'll subtract 1 from the left and 1 from the right. That will leave us with negative 4 is less than or equal to 2x, which is less than or equal to 2. Now the last step to isolate x in the middle will be to divide by 2. And if we divide the middle by 2, we have to divide the left and the right by 2. This will leave us with negative 2 is less than or equal to x, which is less than or equal to 1. If you're asked to write your final answer in interval notation, you might find it helpful to graph this on the number line. This means that x is between negative 2 and 1. So let's find negative 2 on the number line, and I'm just going to put a dot there for now. And we'll find 1 on the number line. And x is between negative 2 and 1, so x can be any number along this line. And then as we learned in our chapter 2.5 video, if you see less than or equal to symbols or greater than or equal to symbols, we use brackets on the number line. So we'll put a bracket next to negative 2 and a bracket next to 1. Now to write our final answer in interval notation, we always start with the lowest number, which is negative 2. Then we put a comma and list the highest number, which is 1. So if you plug any number in this region in for x and then compute this quantity will be less than or equal to 3 units from 0. Another way to look at this is if you take any number in this region and plug it in for x into this original inequality, you'll get a true statement. Let's take a look at another example. Remember, so far, we've only discussed how to solve absolute value inequalities involving less than or equal to symbols. The first step with any absolute value problem is to isolate the absolute value expression. So let's start by copying down our original given problem, and we want to isolate this absolute value expression right here. So to do that, let's subtract 4. And that will leave us with the absolute value of 2 minus 5x is less than 7. Now we've isolated the absolute value expression. Step 2, if the isolated absolute value expression involves a less than or equal to symbol, which is the case here, then we want to rewrite the inequality as a compact double inequality. So let's start by copying down this exact inequality right here. Now, again, the absolute value means distance from 0. So in order for this quantity to have a distance from 0 that's less than 7, this quantity must be between positive 7 and negative 7. So this is our compact double inequality. Now we just have to work to isolate x in the middle. Let's start by subtracting 2. That will leave us with negative 9 is less than negative 5x, which is less than 5. Now, to isolate x in the middle, let's divide by negative 5. Remember, with inequalities, if you multiply or divide by a negative number, you have to flip the inequality. So since we're dividing by a -5, let's flip this inequality, and we'll flip this inequality. And -9 divided by -5 will leave us with a positive 9/5. These -5's will cancel, leaving us with x, and 5 divided by -5 will give us a -1. So this says that x is between -1 and 9/5. To convert this answer to interval notation, you might find it helpful to graph this on the number line. And to help us graph this on the number line, I'm going to convert this to a decimal. 9 divided by 5 gives us the decimal 1.8. And I'm going to start by just making a dot around 1.8 on the number line, and then I'm going to make a dot at -1. So this says that x is between -1 and 9/5, so x is any value along this line here. And now we have to decide if we use parentheses or brackets at the endpoints. With less than symbols or greater than symbols, we always use parentheses. So I'm going to put a parenthesis here and a parenthesis here. Then, for interval notation, we start with the lowest number in our answer, which is -1, and we'll use a parenthesis. Then we put a comma and list the highest number, which this was 1.8, or in other words, 9/5. And we'll use a parenthesis here since we see a parenthesis at 9/5. Now, so far, we've only solved absolute value inequalities that involved less than or equal to symbols. We will end by discussing how to solve absolute value inequalities that involve greater than or equal to symbols. Let's start with a very simple example to help us explain the process. So we're asked to find when is the absolute value of x greater than 4. Remember, absolute value means distance from 0. So what's another way we could phrase this statement? We need to find all real numbers, x, that have a distance of more than 4 units from 0. The absolute value, or in other words, the distance from 0, must be more than 4. So what numbers on the number line are more than 4 units from 0? Any number in this region is more than 4 units from 0. For example, 5 is a distance of 5 units from 0. That's more than 4. 8 has a distance of 8 units from 0. That's more than 4. But also, any number in this region has a distance of more than 4 units from 0. For example, -6 has a distance of 6 units from 0. That's more than 4. -10 has a distance of 10 units from 0. That's more than 4. So how could we write this information using inequalities? In order for the absolute value of x, or in other words, the distance from 0, to be greater than 4, x must either be greater than 4 or x must be less than -4. So, if you see an absolute value inequality involving a greater than or equal to symbol, you're going to need to rewrite the problem as 2 separate inequalities involving or, which is exactly what we did here. Now, you'll often be asked to write your answer using interval notation. Remember that in mathematics, or means union, so we're writing our answer as the union of these 2 sets. And to do that, we'll first describe this using interval notation as -∞ to -4, and then we'll put our union symbol and then describe this as 4 to infinity. Before we look at our next couple examples, let's write the general rule for solving absolute value inequalities involving greater than or equal to symbols. If you have the absolute value of some quantity is greater than a, we solve this by writing the 2 inequalities, u is greater than a, or u is less than -a. If you have the absolute value of u is greater than or equal to a, we solve this by writing 2 very similar inequalities. We say u is greater than or equal to a, or u is less than or equal to -a. So let's solve this absolute value inequality right here. The first step of any absolute value inequality is we need to isolate the expression containing the absolute value. So I've started by copying down the original problem. Now we want to isolate this absolute value expression right here. To do that, let's add 14. And that will leave us with the absolute value of -10x minus 6 is greater than 14. So we've successfully isolated our absolute value expression. Now let's move on to step 2. If the isolated absolute value inequality involves a greater than or equal to symbol, which is the case here, Then we're going to rewrite the inequality as two separate inequalities involving or. So I'll start by copying down this isolated absolute value inequality. Now, we're going to write two separate inequalities involving or. The first inequality is the easiest to write. You just copied this down exactly, but remove the absolute value symbols. That will give us negative 10x minus 6 is greater than 14. The second inequality is almost just as easy to write. We start by copying down negative 10x minus 6, and then we make two changes. We make this 14 negative, just like we practiced with absolute value equations. And we also flip the direction of this inequality. So it becomes a less than symbol. And then we put an or in the middle. So this says that the absolute value of this quantity must be greater than 14. Another way to phrase that is that the distance between this quantity and 0 must be more than 14. In order for the distance between this quantity and 0 to be more than 14, this quantity must be greater than 14, or this quantity could be less than negative 14. So now let's go ahead and solve each of these inequalities separately. I'll start by solving the inequality on the left. Notice we're dividing by a negative number here, so we have to flip the inequality. And that will leave us with x is less than negative 2. Next, let's solve this inequality on the right. And again, since we divided by a negative number, we have to flip the inequality. And negative 8 divided by negative 10 simplifies to a positive 4/5. Now, we're asked to write our answer in interval notation. To write your answer in interval notation, you might find it helpful to graph this on the number line. Let's start by graphing x is less than negative 2. So let's find negative 2. And remember to use parentheses for problems involving less than or greater than symbols. So we'll draw a parenthesis, and we'll draw our arrow going to the left to show values less than negative 2. Then let's represent this on the number line. If you take 4 divided by 5, you'll get 0.8. So 0.8 on the number line will be right about here. We'll use a parenthesis. We'll draw our arrow going to the right to show values greater than 4/5. Now we need to represent this answer in interval notation. We learned in chapter 2.5 that the word or means union. So for our final answer, we're supposed to find the union of these two sets, and the union just means all of this solution as well as all of this solution. So we can represent this region in interval notation as negative infinity to negative 2, and then we put our union symbol, and then we can represent this region in interval notation as, let's see, this was at 4/5 or 0.8, so as 4/5 to positive infinity. Now before we look at one last example, I want to make sure we understand the two types of absolute value inequalities. Let's look back for a minute. First, we learned how to solve absolute value inequalities involving less than or equal to symbols. We said with any absolute value problem, you always first isolate the absolute value expression. Once you've isolated the absolute value expression, if you see a less than or equal to symbol, you then write your problem using this compact double inequality. Next, we looked at absolute value inequalities involving greater than or equal to symbols. If, once you've isolated your absolute value expression, you see a greater than or equal to symbol, then you solve this inequality by writing two separate inequalities involving or. So you have to decide, does your inequality involve a less than or equal to symbol? Or does it involve a greater than or equal to symbol? Because that will tell you how to solve the problem. Now be careful. When determining how to solve your problem, you want to look at the inequality of your isolated absolute value expression. Don't look at the original inequality. Sometimes when you're isolating your absolute value inequality, you might multiply or divide by a negative, which would cause the inequality to flip. In that case, the original inequality would be a different direction than the isolated absolute value inequality. So make sure when you're deciding what type of problem this is, look at the inequality of the isolated absolute value expression, not the original inequality. Let's do one last example. So first step, we want to isolate the absolute value expression. So I'll start by copying down the original problem, and we want to isolate this absolute value part right here. So to do that, let's start by adding 3. And then the last step to isolate this absolute value expression is to divide by 4. Now we've isolated our absolute value expression. Now we can move on to step 2. In step 2, we look at the direction of our inequality, and that will help us determine what type of problem this is. If this were a less than or equal to inequality, we would solve this by writing compact double inequality. But that's not the case here. Instead, this is a greater than or equal to symbol. We know that if the isolated absolute value inequality involves a greater than or equal to symbol, which is the case here, then we rewrite the inequality as 2 separate inequalities involving or. So I've started by copying down this inequality that we left off with, and now we want to rewrite this as 2 separate inequalities involving or. The first inequality is the easiest. We just copy this down exactly, but remove the absolute value bars. Then we'll put an or here, and then for our second inequality, we start by copying down the negative 2x plus 1. And now be very careful. We make 2 changes. We flip the direction of this inequality, and then we make this 1 negative. Now we just need to go ahead and solve these 2 inequalities. And we're left with x is less than or equal to 0. Which leaves us with x is greater than or equal to 1. Now, to write our final answer in interval notation, I'm going to go ahead and graph this on the number line. X is less than or equal to 0. We'll draw a bracket at 0 and our arrow going to the left. And then x is greater than or equal to 1. We'll draw a bracket at 1 and our arrow going to the right. Again, the word or means union, so for our final answer, we describe all of the solutions in this set as well as all of the solutions in this set. We can describe these solutions as negative infinity to 0, and we can describe these solutions as 1 to infinity. So if you plug any number in this interval, or any number in this interval, in for x into the original problem, you'll get a true statement.